Well done. You have finished the main lecture material for week one. So what have we seen this week? Euler-Lagrange equations as an alternative for Newtonian mechanics. So we revisited a bit of Newtonian mechanics and Newton's second law, F equal ma. But importantly also how you get a force from a potential, because this relationship between force and potential um, is important to show the equivalence between Newtonian mechanics and Euler-Lagrange equation. So as you can see in the Euler-Lagrange equation, you have um, a bunch of quantities which we need to define. The first one is a Lagrangian, and you have seen that this is a difference between the kinetic energy and the potential energy. And that's not the same as the total energy, which will have a plus instead of a minus. But the quantities, the kinetic energy and the potential energy, are the same. So for one particle, for instance, it's just half of mv squared for the kinetic energy. And the potential energy will be, for instance, the gravitational potential energy or the potential energy of mass attached at the end of the spring, which is a harmonic oscillator, k x squared on 2. You also see that in the Euler-Lagrange equation, you have partial derivatives and total derivatives. So we have seen the difference between the two, and that's very general and important concept, which we'll see in other areas as well. We have seen that Euler-Lagrange equation can be used with any kind of coordinate, so that we call that general coordinates. You can use them, for instance, with spherical coordinates or polar coordinates, more precisely, which is what we have seen this week. One difficulty with polar coordinates is how to express the velocity and the kinetic energy. So we looked at that in some details, and now that you should know how to get these equations for v and k, but now that you have done it once, you don't need to do it again. So every time you need kinetic energy or velocity in polar coordinates, you can just use these expressions without rederiving them. And the application for that was essentially towards pendulums, but there is plenty of other examples where Euler-Lagrange equations are useful.